Can you hear me in the back? Yes. Wonderful. It's a great honor to be invited to talk here to you, and what you see here is a drawing that I made almost 20 years ago about a robot that has a model of the world, and this model of the world also includes the robot itself, and it includes the world model of the robot itself. So recursively, you have this recursive deep chain of world models in a system like that, which is thinking about the future to optimize the future action sequences through planning. And there you will see how to pronounce my name, how to help the chairman pronounce my name. And today, many people are talking about generative AI. Generative AI, which has taken the world by storm, as large language models are creating texts which are almost indistinguishable from what humans produce. And I'm quite pleased about that, because the stuff that is driving these large language models is a neural network, an artificial neural network called a transformer. A transformer. Does anybody know what is an artificial neural network? Hands up. Okay, so we have two guys who know what is an artificial neural network. Does anybody not know what is an artificial neural network? We have a third group in this room which didn't understand the question. So an artificial neural network is something a little bit inspired by the human brain. In the human brain, you have got 100 billion different little processors they are called neurons, and each of them is connected to 10,000 other neurons on average, roughly, which means you have 1 million billion connections in your brain. And some of these neurons are input neurons where video is coming in and audio, just numbers that are coming in, and tactile information and so on. And then some of these neurons, they are output neurons, and whenever they get switched on, then your fingers move or your speech muscles. And all your life is about transforming the incoming data stream into actions such that special inputs are maximized. The special inputs are your reward signals. You want to maximize reward, and you want to minimize pain until the end of your life. That's your goal. And how can you build artificial systems that do the same thing? Well, we also have these artificial neural networks, and some of these connections, through learning, they get stronger, and some of them get weaker. So each connection has a strength, which says, how much does this neuron over there influence that neuron over there at the next time step? And then by making some of them stronger and some of them weaker, the system is learning interesting things, such as driving a car or recognizing speech. And what we see here, some people think that transformers go back to 2017 to Google, but that's not true. The first transformer type was published in 1991. I called it a fast weight controller. Today it's called an unnormalized linear transformer, but back then I didn't call it a transformer, I called it a fast weight programmer or a fast weight controller. It's doing exactly the same the thing that modern transformers are doing, except that it scales linearly. It's called a linear transformer because it scales linearly. What does that mean? If you have 100 times more input, then you need only 100 times more compute to solve that. With the modern quadratic transformers, you need 100 times 100 is 10,000 times more compute. So the modern transformer, they scale quadratically rather than linearly. And this is really important, I think, because many people are trying to overcome this limitation of the recent transformers, and they want to make them more efficient. And so a good way of starting is look at the linear transformers back then of 1991. So also there, you have a network that sees the incoming data, and then it learns to generate keys and values, and these keys and values are used to create a fast weight mapping in a part of the neural network that learns really quickly, that has very fast weight changes, which are then being applied. So these mappings are being applied, these attention mappings are being applied to the queries that are coming in. For example, predict the next word in this chat. Stuff like that. And I'm rather happy that the G and the P and the T of GPT, they all go back to our miraculous year, 1991, back then in Munich. So not only the T in transformers, but also the P, the pre-training, because back then deep learning didn't work. And what I did then was to compress sequences by predicting the next thing in a self-supervised fashion, such that the prediction machine was able to compress greatly these sequences, such that suddenly deep learning became possible where it wasn't possible before. And in the same year, or actually in 1990 already, I had these things which are now called generative adversarial networks. I didn't call it generative adversarial networks, I called it artificial curiosity. But there you have these two networks and they fight each other. So one of these networks is generating outputs probabilistically. So there is an output probability distribution over possible outputs. Can be anything. And there's another network that sees these outputs of the first networks as inputs and is trying to predict the consequences in the environment. So the second network is trying to minimize its error, becoming a better predictor, but the first network is trying to fool the second network, is trying to surprise the second network. How? Well, it's trying to maximize the same error that the second network is minimizing. So you have a fight between these two networks, and a game, a minimax game, and this is today very popular for making deepfakes, images that look very realistically. So I'm happy about the fact that the G and the P and the T in GPT all go back to our annus mirabilis, 1991 in Munich. And back then, the long short-term memory, which was also mentioned, also had its roots there. Because there you had to look at the diploma thesis of my brilliant student, Sepp Hochreiter, which already contained the basic principle of the LSTM, which is the residual connections. Residual connections are the thing that make these LSTM recurrent networks really deep. And deep learning is all about depth. Yeah? So there was a time when deep learning didn't work. We had only shallow networks. And then the first recurrent networks that were really deep, that were the LSTM networks. Why? Because they had these residual connections. And then the name 1995, I invented that in 95, but names are not important. The only important thing is the math behind the thing that you are naming there. And so all of this residual connection stuff has become really important, not only because the LSTM is now the most cited AI of the 20th century, but also because something that we published much later, in 2015, the highway network, is working using the same principle, except it's not working for recurrent networks, but for feed-forward networks. So recurrent networks have these cycles, but feed-forward networks are just deep, many layers. And then we use the same residual connections going back to 1991 to make these highway networks really, really deep. And then a variant of that was published half a year later by Microsoft, and this has become the most cited AI of the 21st century. But it's based on the same principles, these residual connections. So this was really a good year back then, 1991, and back then, however, we couldn't do much with that. We couldn't do much with that because computers were so slow. Computers were so slow, but back then we had a friend. The friend was a trend, and this trend basically said every 5 years, compute is getting 10 times cheaper. Every 5 years, compute is getting 10 times cheaper. This trend was old. when I did my diploma thesis in 1987, because it goes back to at least to the year 1941, when Konrad Zuse, this guy here behind me, created the first program-controlled general-purpose computer. In Berlin, he did that. In 1936, he had the patent application. In 1941, he was finished. The first program-controlled computer could do roughly 1 operation per second, 1. And then, 10 years later, you could do 1 million operations for the same price. And when I did my diploma thesis on AGI in 1987, we already had a factor of 1 billion. We could do 1 billion instructions for the same price. And soon, not yet, but soon, we will be able to do 1 billion instructions for the same price per second. And that's the reason why everybody is now using on your smartphones these techniques that were all invented in the previous millennium. So deep learning, all the basic principles of deep learning were invented in the previous millennium. There's very little that has come in the new millennium. Deep learning is an invention of the previous millennium. So by 2009, compute was cheap enough, and we could start winning competitions through the efforts of my PhD student, Alex Graves. 2009, for the first time, computers were fast enough that such that the old methods from the previous millennium could outperform all the other techniques. And then in 2010, I had this brilliant postdoc from Romania, and he was able to make convolutional or other networks really fast on NVIDIA GPUs. 2010, no supervised, unsupervised pre-training, just deep networks, standard thing going back to the 70s of the previous millennium, of the previous century. 1970s, backpropagation was invented in 1970 by Seppo-Linna Inma, the guy in Finland. And then applying this old stuff to neural networks in the same way that has been done for decades, however, making it really fast. And suddenly we were able to win all kinds of competitions. So Dan was then suddenly the one who broke the MNIST benchmark record, which today nobody cares for. But back then it was important because compute was about 1,000 times more expensive than today. And then in 2011, our deep convolutional neural network had the first superhuman result in a competition in Silicon Valley, where it was about image recognition. And, you know, that was long before the AlexNet, and since then, everybody has been using that. Now, again, CNNs, convolutional neural networks, are old stuff from the previous millennium. Go back to 1979 when Fukushima in Japan published the first convolutional network, and then Weibel also in Japan, a German guy working in Japan. In 1987, he combined convolutions and backprop, so Fukushima didn't use backprop. And then Zhang, also publishing in Japan, 1988, he had the first two-dimensional convolutional networks like the ones that we are using today, combined with backpropagation. So between 1979 and 1988, the CNNs were created, and all they've been waiting for was make them faster using NVIDIA GPUs. And that's why NVIDIA is now so incredibly successful, because they have the hardware, the shovels that you need to make AI work. Now, by the mid-2010s, LSTM was on every smartphone, on yours too, Alibaba and Samsung and Huawei, and everybody was using it for speech recognition, automatic translation. I still remember 10 years ago, 15 years ago, I came to China and I had to show the taxi driver a picture of the hotel such that he knew where I wanted to go. Today, he holds his smartphone into my face and I speak in English or another language, and he gets the answer in Mandarin, and we have a discussion. And the nice thing is that language barriers, not only between people, but between entire nations, have broken down. So I'm very happy about that. The taxi driver probably has no idea that this stuff was invented in my little lab in Munich and the other one in Switzerland, but it's really broken down communication barriers between entire nations. I'm happy about that part. So The first large language models, they were based on LSTM, and that was until in 2017, the Transformers took over, Transformers 2017, 18. But they also go back to our year of 1991, the miraculous year that we had back then. I'm really happy that all of this AI stuff that we have created, LSTM and fast CNNs and highway networks and ResNets and so, that they are really, really useful in medical applications. And you find thousands of papers, if you search for that, that have, for example, some disease like diabetes in the title, plus LSTM, which is used to predict or to heal that disease. So lots of applications, also in all kinds of additional sustainable development goal use cases. So that is really good. The important thing that I want to mention, which I also mentioned in the AI4S forum just a few minutes ago, is that we cannot only use these techniques to do supervised learning. There's a teacher who tells the system what to do, and then it imitates what the teacher does. No, we can also use it for reinforcement learning, which is much more general, because there's no teacher which tells the system what to do at which point in time. And for that, you need a reinforcement learning technique such as policy gradients to optimize the weights of the LSTM. But that is working really well. We started that in 2017 with my PhD student, Dan Wierstra, and he and his friend, Shane Legg, both in my lab. They were the first guys at DeepMind who really had PhDs in computer science and publications in AI. And they... one of them was the co-founder of DeepMind, the other one the first employee. And then years later, they used it to build video game players that were much better than what anybody had before. And one has to know that video game playing is much harder than chess or Go, because in chess or Go, for example, in chess, you just have a little tiny 8x8 pixel thumbnail, which tells you everything you need to know about the best possible move. But in video games, you have to have a memory of what happened in the past, so this doesn't work. And so you need a recurrent network like LSTM to have a memory, to learn memories of the important things that happened. And then OpenAI used the same thing, an LSTM with 84, which is surrounded by other networks, but 84% of the parameter count is really the LSTM, which is learning by policy gradients to become a good Dota player. So Bill Gates called that a huge milestone of AI. Now, what's currently working well is the AI behind the screen. The only AI today that is working well is the AI on the desktop, behind the screen, in the virtual world. So all the large language models and so on, all you can use them for is to summarize documents, make PowerPoint slides, and all this stuff, and illustrate articles and summarize other articles in a way that allows you to greatly facilitate what reporters do and journalists and so on. However, these large language models, they are super limited. They are just a convenient way of addressing the knowledge of mankind in a way that is convenient because the addressing method is natural language. But of course, it's far from AGI, because for AGI, you need decision makers and you need to have AI in the physical world. Now, AI in the physical world is much, much harder than AI in the virtual world, because if you have a million or a billion trials in a video game, for example, and you die again and again, you get always resurrected. But in the real world, you do 3 experiments with a robot, and the tendons of the robot are broken. So in the real world, you have to deal with extreme constraints that make everything much, much more difficult than in the virtual world. That's why we founded this company 10 years ago, Nascence, AI for the physical world. And there's another company which we are currently pushing, which is using AI for the physical world for automatic inspection. And the company is called Delite, and it's making a superior product for automatic inspection, a machine that is maybe 2 or 3 years ahead of the competition, which can inspect all kinds of food or chips or automotive parts in a way that no other machine at the moment can do, because it combines the hardware and the AI in a way that is patented and has all kinds of tricks that make it really hard to replicate. If there are any investors in the room, we are currently trying to scale that up. So if you are an investor, contact me afterwards. We want to capture a big part of the $3 billion automatic inspection market. Now here, what you see there is the basic principle that I mentioned before already in the AI for us talk that goes back to 1990, which is if you have an AI in the physical world, then this AI, a neural network usually, has to control the robots in that physical world, and it has to learn through a separate world model to predict the consequences of the actions of this robot. And then you create a better and better model of the world. I called it world model in 1990. So this is not a recent notion. It's an old paper from 1990. And this world model can be used as a planner. So once you have a good model of the world, you can use it to plan action sequences in counterfactual reasoning ways. You just say, what happens in my mental simulation if I execute this action sequence? What happens if I execute this action sequence? Oh, with this action sequence, I don't run into this obstacle, so I don't feel pain. So it's much better than the other action sequence, and I'm going to take that one to optimize my performance in the future. So that goes back to these old papers, again, to this miraculous year, 1990. And the important thing is, in the beginning, the controller is creating actions, and there are consequences of the actions, but the model of the world knows nothing about that. So the world model is stupid. How can I incentivize the controller to generate action sequences that lead to data that improves the model of the world? And back then, the simple idea was, okay, the error of the world model is the reward of the controller. So the controller is maximizing the same thing that the world model is minimizing. So we have something that is now called a generative adversarial network, a GAN. And you can use it to build robots that set themselves their own goals through artificial curiosity. That's how I called it back then, artificial curiosity. And then we had all kinds of applications through the decades with real robots of these concepts. And there is a problem, however. The problem of this approach, which is still being used, widely used, is it's about millisecond by millisecond planning. And that is stupid. For example, if you want to go from Shanghai to what is a good place? Where do people go from here? To Paris. My next stop is Paris, actually. So then you don't create a plan in your head which goes like this. Move your little pinky a little bit, just like this, until you reach your smartphone, and then call the taxi station, and then call the taxi, and then once you are at the airport, move a little bit your feet to walk to the check-in counter. No. What you really do, you as a human, you have a high-level, abstract way of planning your future. You just decompose the future into a few essential sub-goals. And then you already know all kinds of sub-programs that lead to these sub-goals. And so instead of thinking about trillions of different action sequences, you just look at a few combinations of sub-goals that you can execute in the future. And you already have in your neural network encoded sub-programs that lead from start to sub-goal and from this sub-goal to the next sub-goal and so on. So you're learning to think about the environment in a hierarchical way. And this is what many people today think it's important, but already in 1991 we had the first machines that really could decompose long sequences into chunks and then also recompose these chunks again in terms of subgoals, such that you try to achieve something new that you never have achieved before. And a gradient-based subgoal generator is learning to suggest through the data, through working on the data, to suggest good subgoals. So even that is an old hat, except that we now have better ways of doing that than what we had back then. So this picture here is from 2015, and it's about a reinforcement learning prompt engineer. So this prompt engineer here of 2015, so about 10 years ago, is not any longer doing millisecond by millisecond planning. No, instead, there's the controller, there's still the controller, and then there's the model of the world model. It's called M in this picture, and the M maybe has seen all the YouTube videos. Maybe it's a foundation model, maybe it's something else, but it has a lot of algorithmic information about all kinds of actions, because YouTube is full of movies of robots that throw things, and humans that throw things, and kids that throw stuff. So there's a lot of information in YouTube videos about how to throw stuff. Now, the controller wants to control a robot that has never thrown any ball or something, but what you want to do is you somehow want to extract the information that is in the world model, so you want to address the right parts of the internal representations of the world model in a way that allows you to solve that problem of the controller faster than learning the whole thing from scratch without access to this model of the world. And so what this 2015 thing does, basically, the controller learns to inject prompt sequences of prompts, queries, into this model of the world, which will send something back. And what is the stuff that is coming back? It's just number sequences of vectors and numbers. But now it's the job of the controller to learn to interpret these answers and to learn over time to address the right parts of this huge world model such that its own learning process is facilitated, is sped up. And the ACID test is, does the controller learn the new task faster from scratch without access to the world model, or just setting all the connections to the world model equal to 0 by ignoring it, therefore, or can it profit from the algorithmic information in the world model through learning to address the important stuff there and interpreting the answers that are coming back? So, learning to think. This is a follow-up paper then where the controller and the model are collapsed into a single network using the neural network distillation procedure. Some people think neural network distillation is a recent thing. No, it also goes back to 1991 when I published that for this deep learning system that used predictive coding to facilitate deep learning. So here, this is a more NeurIPS workshop Best Paper Award with a whole bunch of Chinese students at KAUST. A team of PhD students at KAUST, the university with the highest impact per faculty on the Red Sea, and Ming-Chen Zhuge and several other guys on this paper. And this is not only about, a system consisting of two neural networks. One is the controller, the other one is the model. No, now we have an entire society of language models. Up to 100, or actually more than 100 language models. You give them a task that one of them cannot solve, that none of them can solve by itself, but collectively, maybe they can solve it. And how can they solve it? Well, they start something we call a mindstorm. They discuss the problem, and it goes back and forth, and this language model has an idea, and maybe this caption generator about vision, but not so much about thinking. And so they all interact, and there are different ways of organizing them. So you can organize these language models either in monarchies, where there's a neural network king that decides which of the proposals of the underlings are useful and are to be executed. And then you can have a democracy where, the rules of democracy by voting on certain opinions, and in these mind forms, it turns out sometimes for some tasks monarchies are better, and for other tasks democracies are better, and we don't have a general. Very interesting, lots of applications of that stuff. Now, what excites me most about machine learning is really meta-learning, where you not only learn something here and learn something there, but you also learn the learning algorithm itself, and you learn to improve the learning algorithm itself. So you're not stuck with the human-generated learning algorithm. No, the learning algorithm itself improves over time, and the way improves, you improve the way it improves, and so on recursively, without any limits, except for the limits of computability and physics. And my 1987 diploma thesis about AGI was about that. And here you see the image, the cartoon that I drew for the cover of my diploma thesis, 1987. Back then, nobody was interested in that. But today, it's a hot topic. And we have more recent results with guys that you saw on the previous slide. For example, we now have neural networks, and this is work done with Louis Kirsch and others, my student, Louis Kirsch, now at DeepMind. The network learns to implement the backpropagation algorithm on itself. So on the hidden activations of a neural network, of a recurrent neural network, the backpropagation method itself is being implemented. So within the weights, I get a message, my time is up, but I don't believe it. How many more minutes do I have? Only 10 more minutes? Yes. Okay, so we have all this recent new stuff on meta-learning, where backpropagation, for example, is running on the network itself, but then through gradient descent, you propagate through this backpropagation algorithm, and it improves. It becomes a better learning algorithm. So we have examples for supervised learning and reinforcement learning. I think that's going to be the future. My time is up, so I can't even mention the recent work about artificial curiosity with abstract experiments. I can mention it, but I cannot talk much about it. I cannot talk about AI for science. I already mentioned at the other talk and the AI for S forum, these chemistry projects where artificial scientists are used to improve chemistry. And of course, I have no time to mention the people on whose shoulders we are standing. Some people think that neural networks were created in the 50s. No, they go back 200 years, and deep learning is not a recent thing. No, it started in 1965 through Ivaknenko and Lapa in the Ukraine. So here is a tech report which is called Annotated History of Modern AI and Deep Learning. Read that, such that you know where your field is coming from, and such that you know where all these techniques that you are using today are coming from. What's still missing? The thing that is really missing is AI in the physical world. And at the moment, we have these little robots that are like babies in the sense that they are really weak. Lots of sensors, lots of cameras and so, but really weak muscles such that they cannot destroy themselves through their self-invented experiments. And this is also going to scale, I'm sure. It's going to be really important for the future. And then a really important next step will be self-replicating and self-improving societies of machines, and 3D printers and other machines. Probably you know that 3D printers already can print parts of themselves, but we do not have a 3D printer that can print itself, because there are all kinds of parts in the 3D printers which cannot be printed. So it doesn't need a genius to see a future where where a whole collection of machines and 3D printers and robots and machines that repair the robots and all that stuff, at some point won't need humans any longer to make a copy of themselves. Some sort of a machine civilization that can make a complete copy of all the machines that are part of this civilization. We are not there yet, but it's going to get there. And once that is achieved, once you have truly self-replicating societies of robots and other machines, then everything is going to change, because that is the ultimate scaling machine. And the economy of the world is all about scaling, so that is the ultimate scaling machine, and there will be commercial pressure towards that, because those guys who own a scaling machine like that, lifelike machines that can replicate themselves, they are going to become very rich. And such lifelike machines are not going to be limited to our biosphere. Well, they can also survive in the asteroid belt or on the moon or in Mercury and so on. So that is going to change everything, and the economy of the solar system is going to grow by a factor of 1 billion compared to the little tiny thing that we have today in the biosphere. Think about that. This is the near-term future. So near-term means next few decades or something like that. I don't have time to discuss all the incredible things that are going to happen in the next 55 billion, well, in the next 40 billion years, as AIs are going to expand into space, because most of the resources, the physical resources, energy and matter that you need to build more AI and more and bigger AI factories and all that stuff, most of these resources are not here in our little biosphere, they are far out in space. And at the light speed limit, there is plenty of time, to colonize the entire universe, because the universe is still young. It's only 13.8 billion years old, and it's going to be many times older than that. And you need just a couple of tens of billions of years to colonize, through AI, the entire cosmos. And this is going to change everything in a way that is not limited just to our little planet, but that's about the entire universe. So, as I said in a TEDx talk many years ago, this is not just another industrial revolution. This is something new that transcends humankind and even biology itself. And there's beauty and grandeur in realizing that humans are just a step and not the last step on the path of the universe, from very simple initial conditions to more and more unfathomable complexity. That's going to be the future. Here we have a very nervous organizer who wants me to stop, and I'm going to stop now. Thank you for your attention.
Thank you, Jürgen.